First of all, I'd like to thank all of the entities for attending, of course, and the organizers for organizing this iteration of Hot Interconnect. Um, what I'm going to do today um, is divided into three parts. I'll give you a high-level overview of what we call Bittide and what it promises to do. And I'll then give you an overview of the first time implementation we built. And finally, I'll go over the measurements we took and how we can interpret them. Um, of course, I very much hope you guys enjoy it. And I'll hop on the Slack channel after the presentation to answer any of your questions. But feel free to spam in the meantime. All right. So, Bittide for me in one sentence is clock cycle accurate synchronization at data center scales. The basic idea is that we can build a system of interconnected nodes of which we can guarantee that the clock cycles of any one node in the system are aligned with the clock cycles in any other node. That is to say, we can perfectly predict when data frames will arrive at any node in the system. We can reason about the timing of computations, and all of this we can do down to the clock cycle. So right away, I'm going to give you a few promises. And at the end of the talk, I hope that you guys are convinced that those promises actually hold. We can do ahead of time time scheduling of all communication in the system, riding on the current interests of the industry and what the keynote also pointed out is that this stuff is an almost perfect fit for AI workloads, whose in-burst computations and communication are both highly predictable, but also highly parallelizable. So in a sense, the system that I will show you in the rest of this presentation brings the benefits of a single chip design to data center scales. This, of course, also means getting rid of tail latencies entirely. The second promise that I'll make is that we can do this all with zero in-band overhead. That is, we don't need to send any additional data frames to keep the system synchronized, and we don't need to do any handshakes, polling, that kind of stuff. We also do this in a completely decentralized manner, meaning that we don't synchronize to a global clock. We don't hierarchically derive clock signals, and each system or each node in the system is basically self-contained and can operate independently. Above all, it is simple, both in its theory. There are no complex state machines and synchronization protocols, but also in its hardware implementation. With these promises out of the way, let's have a look at how this actually works. So, what I want you to imagine is a system of interconnected nodes. And for now, I've drawn up a very simple system consisting of two nodes. And each node has a small buffer on its incoming link. For the sake of argument, and I'll get back to that, let's assume that all of these nodes operate on the exact same clock frequency, and that the buffers, so the FIFOs, are filled halfway through. What do we expect to happen in a running system? Well, not that much. Every time a node pops one item of the FIFO, another one gets placed at its rear end. And this is a natural consequence of the definition I made in the beginning that these clock frequencies are the same. In this system, we can measure a mapping from one node to another. If a data frame is sent at a local clock cycle P from one node, it will arrive at clock cycle Q at another. The difference between those two numbers is really only affected by the offset in power up. So one node might boot a little bit later than the other, and so you get a huge difference in the clock cycle counters. But crucially, this number will stay exactly the same during operation. Now, note what we can do with this property. We can statically schedule computations in communication. Um, and I'll go a little bit further and say that these FIFOs, if we loosen our assumption that the clocks are exactly equal, can even absorb a little bit of clock frequency wobble. That is to say, the logical latency between two of these systems will remain the same until the buffer overflows or underflows. And so, of course, real clocks aren't exactly equal. Their frequencies differ, their clock wobble difference, and so this is a nice thought exercise, but it's not really sensible in practice. And so what we'd like to have is a system that keeps these clocks under control. And so the idea is simple. Again, we start with the buffers half full. When we notice the buffers start to fill a little bit, we speed up because we conclude that compared to the rest of the network, we're running too slow. Conversely, when we notice the buffers start to drain, we conclude that we're running too fast in comparison to the rest of the network, and we instruct our clock to run a little bit slower. And so what we've done, in a sense, is build a distributed PLL this way. Now, if clock control is successful, these FIFOs will remain within their bounds, preferably at their midpoints, and the logical latency between any two nodes will remain the same. And so we can now think of our network in graphs like this one, where the vertices represent the nodes and the edges represent the logical latencies between them. Note that the logical latencies can go negative. So that happens when one node boots after another, and that these logical latencies don't really make sense. I've tried to make a point out of it by picking these really large numbers. But the idea is that a cycle through a graph, so any path through the graph that starts at the same node and ends at the same node, will have this, will be positive and will also be relatively small. And it's indicative of the latency through the network. But again, constant, because we keep these buffers approximately halfway full. So, onto the implementation. What did we build? Oh, sorry. We start with 8 FPGAs. You can see those in the back. And these are off-the-shelf AMD FPGAs. They're fully connected to each other over 10G Ethernet, and the cables are a mix of copper and fiber. All the cables are 2 meters long, approximately, though in some experiments we replace one pair of cables with 2 kilometers of fiber. In front of these, we have 8 Skywork clock synthesizers. Like the FPGAs, these are off-the-shelf components. And although the specific kit that's shown here is fairly specialized, the clock synthesizers themselves are fairly ubiquitous. We bought them off Mouser, but we later also found out that one of these exact chips was on our FPGA anyway. So, as the name implies, of a clock synthesizer, these parts can generate clock signals. In our specific case, a reference oscillator is part of the board, and it's wired to a PLL. This PLL can convert the reference frequency, whatever it may be, to basically any frequency you'd like, somewhere between 100 mega or 100 hertz and 700 megahertz. Typically, you just set these boards or these clock synthesizers to a single frequency, and you do your thing with that. Um, While we do that too, we also want to tweak the frequency a little bit, like I explained earlier, while the clock is running. And so luckily these boards support that too. And for our experiments, we set the step size of these frequency changes to 10 parts per billion. Um, that means that for every billion clock cycles ticked, the clock synthesizer will add 10 extra and then smear it out over that whole period. And to give you an idea of how mind-bogglingly precise these boards can be, these boards that are fairly cheap uh, support step sizes as low as 1 part per trillion, which is way overkill for our application. The clock boards are connected to the FPGAs in two ways. First, each clock board is connected to a single FPGA and generates the reference clock for that FPGA. And second, the FPGA is then connected back using two wires, and these are connected to the frequency increase button and the frequency decrease button on the clock synthesizers. And we've done some FPGA design to expose these pins then to a microcontroller. Finally, at the very front, you see some external measuring equipment. This is just to get a sense of what we're doing and to generate interesting data for the paper. So now that we know what we have and how it works, let's go to the measurements and the validation that we did. So we start off the measurements by letting a fully connected set of 8 nodes converge from their natural oscillator frequency to a synchronized state. On the x-axis, you'll see time. It might be a little bit smaller on your screen, but it's in milliseconds. And on the y-axis, you see the buffer occupancy delta, or in other words, the offset from the midpoint of the FIFO. And so what you see is that once these boards are synchronized, the buffers stay within a margin of plus minus 2 elements from the converged center points. On the left side is a run where all the cables are 2 meters or less, while the right side, one of the pairs is replaced by a 2-kilometer fiber. Measurements show that this increases the total latency, as you would expect, by about an order of magnitude. But as far as we can see in our experiments, the clock control is just insensitive to this. They're not shown in the paper. We've also done this experiment for long-running tests. We've been running tests over the weekend, and still in those situations, the buffers do not get more than 2 from their midpoints. So that is to say, these systems, when clock control is active, are super stable. So before we go on to the next experiment, I want you to observe that all the buffers show a very specific shape, and that that these shapes correspond. And that's because there are no asymmetries in a fully connected topology. So for the next experiment, we wanted to see what happens in an asymmetric topology. And so we've made 2 clusters of nodes connected over 1 fiber. Like the previous experiment, the system converges to a stable point. Again, the buffers will hover around to around their midpoint. Um, what you can see in the plot then is these artifacts of it not being a symmetric system. So you see some buffers having a different shape than the others. Okay, so now that we've seen that clock control works and these buffers stay in at their midpoints, um, we we can measure round trip latency. And that's what the next table is all about. So what you see is the connections to each FPGA, and for a fully connected topology. So we don't measure loopback connections, and round trip times are by definition symmetrical. And so we leave out a little over half of the table. One point stressing again is that these latencies are counted in clock cycles, and once a Bittide system is booted, they will not change. Um, so what you can see is that our latencies for fairly low speed equipment hovers around 68 clock cycles. Of course, with the one exception being the 2 kilometer fiber optic link. Um, We didn't build this Bittite hardware uh, just for fun and out of a gut feeling. Uh, Quite a number of papers have been published on this already, and also simulators have been built to try to predict what would happen in an actual hardware implementation. Um, and so what this plot shows is a comparison against previously defined models. So the red line is what the model predicts should happen to the clock frequency, and the black line represents what we actually measured. And so you can see a little bit of almost jitter, but this is more a measuring artifact. We can't measure in our current setup that precisely. Um, And so the eagle-eyed amongst you might have noticed that the previous experiments took about 5 or more seconds to converge. But this is a deliberate setting. Like I said, with our current setup, we can't measure all that well. And so we prefer longer timescales so we can make more precise measurements. However, of course, 5 seconds is quite a lot, and for larger networks, you would expect it to take a lot more time. Um, so we've also done experiments where we make clock control much more aggressive. As you can see, this causes a lot more jitter in the plots, and it's somewhat harder to see what's going on. But it does show that clocks can converge within 200 milliseconds too. Um, Now that we hopefully have uh, quite a bit of confidence in our simulators, seeing as they match that well with our actual measurements, for fun, we've done measurements with over 20,000 nodes. So this is a torus configuration, and it shows that these clock frequencies and the buffer occupancies in simulation still converge. And so we expect Bittide to scale out from 8 nodes to 20,000 nodes to millions of nodes. Um, Conclusion. So what we've seen for Bittide itself, the synchronization scheme, we can do ahead of time clock scheduling. We've got zero in-band overhead. It's decentralized, but above all, it's very, very simple. You don't need a lot of hardware to do this. You don't need a lot of software to do this, but you do get all these great benefits of being perfectly synchronized. Our contribution in this paper, we did a first-time hardware implementation. We only used off-the-shelf components. The models that we built earlier very closely match the actual measurements that we did, and clock control, at least for longer running experiments, seems incredibly stable. With that, all what's left for me to do is to thank you for attending this presentation, and I'll hop over to Slack to answer any of your questions.
Right. Thank you again, Martijn, for the wonderful presentation and the wonderful paper. For all the audience, I do suggest you to take even a shallow dive into the paper, which to me it presents a very new paradigm, which upon which we are only probably seeing the tip of the iceberg, but it's exciting to see the direction where this work is taking. Well, thanks again, Martijn.